Hello, I'm Dave Feldman, Professor of Physics and Mathematics at College of the Atlantic in Bar Harbor, Maine. I'm also a member of the Santa Fe Institute's Complexity Explorer team. I'm here to tell you about my online course on fractals and scaling for complex systems. Registration and all course materials are free. The class is open to everyone. We'll begin by looking at fractals as self-similar geometric objects. Classic examples of fractals include clouds and coastlines, mountain ranges, trees, and ferns. Let me say a little bit more what I mean when I say that objects are self-similar. So, a classic example of a fractal would be this fern. So this fern is made up of shapes, and each of the shapes look like the fern. So if I were to take this fern and take a little piece off, what I have left is something that looks kind of like the fern itself. So here's the original copy, and it's made up of small copies of itself. So we say it's self-similar. It's similar to itself. In contrast, a person is not self-similar. If I pull an arm off of a person, what I have doesn't look like a person. It looks like an arm, a creepy little arm. It doesn't look like the person at all. So we say that people, or at least on the outside, are not self-similar, whereas a fern is self-similar, and so is a fractal. Now, it turns out that self-similarity applies to objects that aren't like ferns. They apply to things that aren't objects at all, to distributions. And in order to illustrate that, I'm going to need to use a picture really quickly. Here's a fractal known as the Sierpinski triangle. Suppose I asked you to describe the distribution of triangles in this shape. How many different triangles there were of different sizes. Well, the first thing you might notice is that they're triangles of lots and lots of different sizes. There's one big triangle, there's some smaller triangles, and it's triangles all the way down. Triangles made up of triangles made up of triangles. Just keeps going. But the other thing to note is that there's a certain regularity here. So every time you go down one size in triangles, you see 3 times as many. So here is one triangle, and if I go down to the next size, I see 3 of them. 1, 2, 3. If I go down to the next size, this one, I now see 3 times more for a total of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the distribution that would describe this state of affairs would be said to be scale-free. It's scale-free because there's a certain statistical regularity that holds across all different scales in the shape. So here's where things start to get really interesting, because it turns out that many phenomena in complex systems are distributed similarly to the triangles in that fractal example we just looked at. They're described by scale-free distributions. Examples of such phenomena include the frequency of words in texts, the strength of earthquakes, the popularity of websites, the size of cities. All of these are well approximated by scale-free distributions. So in the second part of the course, we'll learn about scale-free distributions. Scale-free distributions are also known as power laws, and phenomena that are described by these distributions are said to exhibit scaling. They have a statistical regularity that holds across scales. So we'll look at the mathematics of power laws, what power laws mean, and a number of different mechanisms that can generate power laws. In the last part of the course, we'll look at 2 recent applications of scaling to complex systems. The first application or example we'll look at is metabolic scaling from biology and ecology, and we'll end by looking at urban scaling. How do various features of cities change as the city size changes? These are both areas of current effort and debate. And in this course, you'll gain a background so that you can understand this debate and enter into the discussion. There are no prerequisites for this course other than a little bit of algebra. Any difficult topics I'll be sure to review as they come up in the class, and you can always get help online in the discussion forums if you want. So I'm looking forward to this course on fractals and scaling. We'll cover what I think is a fun and important set of topics, and I think you'll enjoy it and find it interesting. I hope to see you in class soon.